When I started preparing for FANG interviews, I realized something frustrating. System design was everywhere blogs, books, videos, but nowhere complete. Every resource explained one piece, but no one showed how everything fits together. So instead of jumping between random explanations, I decided to build a one shot end to end system design blueprint, and that's exactly what this video series is about. This is our day one. Okay, if I asked you to build a website for yourself, what will you do? You'd spin up a server or your laptop basically, install a database, which might be MySQL or Postgres, the web app React, and be done in an hour with Cursor and Cloud these days. It works perfectly fine on your local host 3000 local host with it. But what if I asked you to make a system that works for 10 million people? How will you do that? Suddenly, everything you know about coding itself breaks. Your database locks up. You're not able to do any writes to the database. You're not able to read anything from the database. Your server starts crashing. You start getting random error logs from Spring, which you can't even debug. And you know what the worst part is among all this? You just can't debug scalability. You can't set a breakpoint on a server crash like you can do in IntelliJ or something like that. So the thing is, the 15 millisecond response time will go to unreachable. That you can't reach your server. Your server is down. Something is happening, and you don't know what, and you don't know the reason for it. So well, welcome to the channel. I spent kind of a long time stuck in like some sort of tutorial hell. I read blog posts from Netflix, Google, and Amazon, and read the documentation for tools I didn't even know back in the day how to pronounce. I realized that system design isn't just a book exactly. It's a collection of patterns, battle-tested rules that engineers use to survive. So basically, what we are going to do today, we are going to bridge a gap between a junior developer's side project and a senior architect's blueprint. We are going to create knowledge, or at least absorb knowledge, from the best engineering blogs and industry standards to build a scalable architecture from scratch. I don't believe in slides, not for me personally. I'm going to draw every component, or at least have pre-draw and show how everything fits together. And we're going to talk about some numbers that everyone should know, like why reading from memory is 100,000 times faster than reading from disk, and how physics dictates our architecture, like actual physics. And by the end of this video, we will have a blueprint to take a startup from 0 users to million users without crashing. So let's start at day one. It's a nice day one for a startup. We are launching a startup. We have limited funds, limited time, and 0 users. So basically, in this setup, everything lives in a box. This is the box. This box can be a laptop, a VPS, or anything. And on the box, you might be running a React front end, a Spring backend, Node, Express, whatever you want to run, and a database, something like MySQL or Postgres, which is storing some data. We don't care what kind of data it is. Yes, that's all we care about. What it is doing, not a concern. Now, it is on a VPS. What is a VPS? It's a virtual private server with its own public IP. Public IP means anybody on the internet can just type this IP on the Chrome web browser, and this your React app will open up. So this works perfectly for 100 users. This is perfect for 100 users. It's very simple to deploy. But thing is, this setup that I'm showing right now, this will run into something called a C10K problem. See, you see, in early 2000s, engineers realized that a single server struggles to handle 10,000 concurrent connections. It wasn't just about the CPU speed anymore. It was about how the operating system handles opening files and memory context switching. Even today, with modern hardware, this setup has a fatal flaw, single point of failure. And what is that? This power source. This simple power source. It is a single point of failure. Unplug this VPS. Everything will go down. Your operating system will shut down because it doesn't have power anymore. That's it. Your business is gone. Your 100 users, they're not able to access the website, and you are dead. Nothing personal. That's the con. That's the con of this setup. And fun thing, the components, the app and the database, they're natural enemies. They fight for resources because they're running on the same system. Basically, your app needs CPU and RAM to process logic, and your database needs RAM and storage to actually write to the RAM and then flush it to the permanent storage. So they start competing with each other for resources, due to which your site slows down, users get frustrated, and well, you try to fix it, and the server with 50 millisecond latency becomes unreachable. So well, there is that problem. And you know, we all know how that goes. You say, I'll just fix this one memory leak, and 3 hours later, you're wondering what year it is. We cannot code our way out of it. We need to design our way out of it. There are no best coding practices in the world that will fix this single point of failure problem. So, the first rule of scalability is decoupling. We need to separate our web tier and database tier, which is basically called compute and storage. Now, we'll move the database into its own dedicated server. Now, you might be wondering, why? This is a massive upgrade. I'll tell you why. Because web servers and databases scale very differently. Web server is like a goldfish. It has no memory. It's stateless. It's just a process that takes a request and forgets about it. To scale it, we just need more CPU and RAM. Now, database is like an elephant. It never forgets. It's not supposed to forget. It is stateful. It holds the truth. To scale it, we need more massive amounts of RAM and fast disks. By separating them, we can optimize each hardware individually. Now let's say our user base goes to 5,000 active users. I know, doesn't sound a very big number, but it is 5,000 active users. And for a startup, it definitely is. Now web app lives here. So how will you go about it? We can just say that, okay, we'll just get a bigger machine for the web app. What will happen? Nothing. If we jump to 5,000 users, the users were initially coming here, they'll start going there. And again, we have solved our problem. This is something called vertical scaling. That is increasing the compute node on which the service is currently running. And if it was not clear, I'll just needs CPU and RAM to scale. Needs RAM and storage to scale. So the 5,000 users are coming here on a 10V CPU and 10 GB RAM. It's again a VPS, and say there were initially only 100 users. And when they became 5,000 users, what we'll do? We'll just get a bigger machine for the web app, and we'll just redirect the traffic there. Okay, now you can go there. Nothing special. We are just vertically scaling, basically increasing the compute node on which service lives. But thing is, this vertical scaling is a trap. We can buy a bigger, more expensive monster machine with like 100 GB RAM or 100V CPU, something like that. See, it's a trap. It's seductive because you don't have to change your code. You can just pay Amazon or Google more money, but it gets exponentially more expensive. And eventually you will hit a hard limit because there is no computer in the world which has infinite CPU and infinite RAM on a single node on which a process can run. It's not possible. It doesn't exist. Now, what to do then? Then we come into something called horizontal scaling. Now, what is horizontal scaling? Horizontal scaling. Basically, adding a similar compute node on which the same service runs. Like we can just add another 10V CPU, 10 GB RAM machine, and we can just say, okay, another database instance lives here, another database instance lives here, and another database instance lives here. How they're interacting with each other, we don't care about it right now. We'll pick it up in a later topic. But as we can see, this is infinite. We can actually get infinite amount of machines which have 10V CPU and 10 GB RAM, but we can't get a machine which has infinite CPU and infinite RAM, if that makes sense. And that's the thing. Horizontal scaling is infinite. If we need more power, we can just buy another cheap server. We can have 10, 100, 10,000, anything, and we will just horizontal scale it. Now, how does that happen? How does traffic get distributed between different compute nodes? We'll see it in the next topic. So this is basically our vertical scaling versus horizontal scaling. Nothing fancy here. I'll just write some few things that will make sense later. Our web app is a stateless service. What do you mean by stateless? As I said before, stateless means it doesn't care what's happening right now. It is not storing any data. It's just taking a request, doing some processing, and passing it forward to the database. Nothing fancy. It's not doing anything. It's just processing the request in memory. However, storage is stateful. It is taking some data and storing it in a disk somewhere in some data center. So this is basically horizontal versus vertical scaling. This interaction that you are seeing, we don't need to worry about it right now, how this happens. Okay, so now let's move on to something called load balancer, and we'll study few things like CDN and cache here as well, at least basic introduction of it. Okay, now what is a load balancer? We've got say two more servers to scale it as we studied before, horizontal scaling. Now we have a practical problem. How does user A know which web app node will its request be served by, and how does user B know which node will serve its request? Now user A can't type a different IP for each node, right? Because we can have infinite nodes. So how does that happen? And same is true for user B. So here's something called load balancer kicks in. Now what is a load balancer? Load balancer basically acts as a reverse proxy. It's like a traffic cop. The user only knows the load balancer's IP, public IP of load balancer. Public IP of load balancer, often called ELB, elastic load balancer. Now when a request comes in, say a user A came and asked a load balancer, so where should I go? Then load balancer will check. Load balancer usually use some simple algorithms like round robin, like send request 1 to server A, request 2 to server B, request 3 to, oh my god, making 3 so difficult. The instance number 3. The request 1, 2, 3 can come from anyone, user A, user B. We don't care. But thing is, there are smarter algorithms as well, like least connection. Like if server A is stuck processing like really heavy video upload, then load balancer is smart enough to know, okay, we can just ignore that pod. Let's say web app A pod. This is doing some heavy video processing. It will be like, okay, then let's send the request to B because A is pretty busy there. Now another thing that load balancer does, does something called health check. Now what is a health check? Every backend framework, every mature backend framework comes with something called default endpoint of health check. Now what does health check do? Health check basically tells if the backend that is running, is it running fine or not? Basically, if the load balancer basically hits the health check API, it's a simple get request and it will get two responses. Either it will get a 2xx or a 5xx. 2xx. 2xx means I am healthy and give me work. 5xx means something is going on, don't give me work. That's it, nothing more. If and say web app C has crashed, then when we check the health check API, either we'll get a 5xx or a 4xx. And when the load balancer gets 5xx or 4xx, then it knows that web app C is down. There's something going on. And say web app A and web app B return 2xx. They return 2xx. This guy also returned 2xx, 2xx. But this guy returned 4xx. We don't know what happened, but something happened. Or 5xx, whatever. Then load balancer knows that this is down. So what it will do is it will stop this connection. It will ask the underlying compute service to either create a new node. We don't need to get into details how will that happen for now. Or or either it will start redirecting traffic to the pod A and pod B. That's it. That's what the load balancer does. Nothing fancy here. Now, our web tier is extremely beautiful, if I say so. Now we have to come to the data tier. It's scalable. We can add 1000 servers if we want. But if you look at our architecture, we still have a single database box. If that primary DB crashes, we'll call it the primary database. This primary database crashes, we are done. We lose data. This is unacceptable actually. To solve this, we use something called replication. And some interesting fact, most applications are read heavy. In fact, a common ratio in system design is 100 to 1. For every one time you post a photo on Instagram, which is a write, you view 100 other photos. Read, don't use that much Instagram, but still. So what we'll do, we'll design something called secondary databases. Now what are secondary databases? Secondary database is something which will get data from the primary database and will just be used for read purposes. Now how will that happen? Not a concern for now, but we use something called change data capture or something like that to transfer data. We use something like change data capture to send events from this primary database to the secondary database. Now that's the thing, these are secondary databases, right? These have the same data as the primary database. Now the thing is, if a slave dies or the secondary database dies, we can just spin up another new one. It's not a big deal. If a master dies, then another secondary database can take its place as a primary database. Now thing is, physics isn't instant. It takes a few milliseconds for data to travel from the master or the primary database to the secondary database. So if we update our profile picture then and immediately refresh the page, it will take some time for it to refresh. This is something called eventual consistency. And for social network, who cares? It's fine. But for banks, eventual consistency is not acceptable problem. We go for something like strong consistency. But that's whole another thing. Now, why are we using secondary databases at all? We use secondary databases to serve all our read traffic. All our write traffic goes to primary database. However, all our read traffic, it will come to secondary databases. And that's the thing. The secondary databases will be able to take off the load from the primary database, which is essentially now serving only the write traffic. Now, primary database has basically 100x reduction in traffic as secondary databases are serving the read traffic. That's it. That's why secondary databases are used. There are certain other cases as well, but that's a primary use case, just to serve the read traffic. And we can just scale how many secondary databases we want, and we can just get all the data from as events or whatever change data capture from the primary database, and we can just use secondary databases for reading purposes. Now, our data tier looks beautiful, I say so again, but we can just make it faster. Now, how to go about it? We'll use something called a cache. Now, what is a cache? I'll say a sentence. It's a very important fact. I said it before. Reading from memory is 100,000 times faster than reading from disk. That means a cache is 100,000 times faster than reading from the database. Literally, that's it. And we'll exploit this. We'll add a cache, something like Redis or Memcached. What it will do, it will just basically, before asking the DB, we'll ask the app checks in the cache. Like, do I have this user's profile in the memory? If yes, return it instantly. If no, fetch from the DB, again, the secondary databases, update yourself, and then send it to the web app. That's it, nothing else. Now, for static assets, we use something like a CDN, content delivery network. These are servers basically located all over the world. So instead of using our web app resources, we just store static assets and something on CDN, and they serve the traffic to the user. Mostly these are for static images and stuff, but actually these days we are also using dynamic content caching in CDNs. That's why you might be seeing that URLs are getting more and more complicated these days in browsers, because those are used to get the dynamic content from the CDN itself. And that's a pretty advanced topic. We might cover that in later videos. But this cache thing, this is tricky. Why is it tricky? Because caching is one of the hardest problems in computer science. Cache invalidation. If I update some data from this write traffic, how will I know that I have to update the key or the data in the cache? How to do that? So you have to create some sort of event architecture that updates the cache basically, or just invalidates the data in the cache that okay, this row was updated in DB. Similar thing should be done in the cache itself. Otherwise, the app will just keep on reading the stale data from the cache. That's one of the hardest problems actually, and it's one of the reasons why it's called hardest problem, because it's very hard to debug. Like, you're not able to figure out why this data is being read from Redis and not the database, even though I updated data in the database. And it's difficult to analyze within a Redis because it lives in memory, so it's harder to debug as well. So basically, this looks a bit janky, but I hope you understood. So look at what we have built. We went from a single fragile box, basically this guy on day one, and we were able to. This can be counted as day 10 or day 100, and this can be counted as day 1000. We went from a fragile box that might fail for more than 200 users to a robust replicated architecture with caching layers that will definitely serve millions of people. You think it won't, but this pretty simple setup will be able to serve millions of people. And to realize this is itself a pretty complicated problem in itself. Like, and thing is, here's the catch: the setup works for millions of users, but what happens when you hit 100 million or billion, like at the scale of Google or Meta? Eventually, our master database will also fill up. We can't just buy a bigger hard drive forever. This is where things get scary. This is where we need sharding. Sharding is complicated enough that it deserves its own really good video, to be honest. And in the next video, I was thinking of breaking down the database sharding and consistent hashing. Like, these are the core concepts for system design. So if you learned something today, kindly hit that subscribe button, and hopefully you learned something from this.